So, okay, so hypothesis testing. That first thing, the hypothesis, is a claim or statement about the property of a population. And we just did our activity. The population that we had was a deck of cards. The hypothesis or claim that we made about that particular population was that I was going to have half red and half black cards. That was the hypothesis, right? So then we performed a little test, a hypothesis test, because that is a procedure for testing that claim. And that's really what we did. Our claim was 50% of them are red, 50% of them black. And then we kind of tested that, and I went around and we had 5 cards pulled with replacement, and we found out that every time we drew, we got black. Well, I tested that. And we failed. See if it says here, rare event rule for inferential decisions. If under given assumptions, the probability of a particular observed is exceptionally small, we would conclude that it is not correct. Okay, but that's just one of the rules. Notes for forming your own claims and hypothesis. You are conducting a study. You want to test to support the claim. And that's what we did. Our claim was at 50% black and 50% red. We are doing the hypothesis to support the claim. Draw a card, replace it. Draw a card, replace it. Draw a card, replace it. And we did that 5 times. Now, if we had 4 black and 2 red, that would probably be okay, wouldn't it? That wouldn't be a rare. That wouldn't be something that would be in a critical region of 0.05 or less as far as the probability. But we did 5 times and got 5 black cards. And that probability would be 1/2 to the 5th, 1/32, or 0.03125. So we know that's the critical reason. That's rare. That's unusual. We already know that. So we tested our claim. Our claim was they were half and half. We drew the card to test that claim. We wanted to support it, but we ended up being able to reject it. And that's how you have to state them. Null hypothesis, and here's that NULL, null hypothesis. We are going to be signifying that with H with a little subscript of 0. That means null. Okay. It's a statement of the value of the population parameter. We could use a proportion, a mean, or a standard deviation. Well, in this class, we're only going to be testing around the mean and the proportion. The mean and the proportion. We will not be, in this class, around a standard deviation. That's a chi-square test. We will test the null hypothesis directly, in the sense that we will assume that the null hypothesis is true. We're going to state it so that we want the null hypothesis to be true. That's how we're going to test it. Then, after we did our test, we drew 5 cards. We need to reach a conclusion. This is the only conclusions that you can do. You're not proving anything, and that's where students have a hard time with hypothesis testing. We are not proving the null hypothesis. We're not proving the null hypothesis. All we're doing is that we're either going to reject it or fail to reject it. In our situation, where we come up to 1/2 to the 5th, or 0.03125, it was so unusual, we could reject our null hypothesis because the null hypothesis says it was 50-50. We tested it, it wasn't. Okay? If it had been, we picked 2 red and 3 black, I can't say I proved it. I cannot say I've proved it. Instead, I would say that we failed to reject it. I can't say I proved that there was 50-50. All I can say is that I have failed to reject the null hypothesis, which says there are 50-50. Okay? Well, we also have to write an alternative hypothesis. When we do that, we can denote it by H sub 1 or H sub A. Most of the time I'll use H sub 1 because that's what I did when I was learning it. And that is that a statement that that parameter, if it's a proportion, or a mean, is different from the null hypothesis. Here's a key thing to know. Your null hypothesis will have an equal sign. Your alternative hypothesis will either have a greater than, a less than, or a not equal to. In the case where we just did with the cards, our null hypothesis was that the proportion of red to black was 50%. Our alternative hypothesis would be that the proportion is not equal to 50%. Okay? There's the or equals to part. Okay? So here's some steps. The first thing we do is identify the specific claim or the hypothesis. And right then and there, we're going to write it in symbolic form, meaning that P is equal to 0.50. That was our symbolic form. Give the symbolic form that must be true when the original claim is false. In our case, P does not equal 0.50. That would be my alternative. Sometimes it'll say less than or greater than in our wording, and that's when we would choose less than or greater than. Okay? And then there's where it's saying that the alternative hypothesis, it cannot contain equality. I'm not going to have the equal sign in there. It can't be any equality. So that H1 uses either greater than, less than, or equal to. So here was another example. Assume that 100 babies are born to 100 couples treated with the X sort method, bless you, of gender selection that is claimed to make girls more likely. Right then and there, what am I looking at? Gender selection, it's claimed to make girls more likely. Right there you should think, my null hypothesis has to be an equal, doesn't it? My alternative hypothesis is going to use greater than, less than, or not equal to, correct? If it's more than, what do you think I'm going to use? Greater than, because it says more likely. That's my clue that my alternative hypothesis is going to be greater than. I know my null hypothesis has to be equal. So, In the test, they observed that 58 girls in 100 babies write the hypothesis test for the claim, the XSORT method, the proportion of girls is greater than the 50%. Well, is it? 58 over 100 is 58%, right? But is that still by chance? Or did this make a difference? That's really what we're testing. So is it unusual that there's 58 out of 100 or 58%? Ooh. You know? So that's really what we're testing, isn't it? So without treatment, there's my null hypothesis, and it has the equal to. The proportion of girls to boys should be 50%. That's my null hypothesis. My alternative hypothesis is written here, and it's written as greater than, because of the wording here, it says more likely. That's how I know what my symbol is going to be for the alternative hypothesis. Again, it could be greater than, less than, or not equal to. Okay? Once we've done that, we have to select the significance level of the test, our alpha. And we've done alpha before. We've looked at those critical values and where it needs to be. And we want to put our values based upon the severity as if we make a mistake. So when I look at the XSORT method, is there any real severity, like to an extreme, that if I made something wrong, if I tested and came out wrong, maybe a couple's going to spend money to use the XSORT method and not going to get a girl, but in the same respect, is that going to harm anybody's life? Is it a medication thing? Is it a procedure thing in medicine where I would need to be really, 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 really sure? So we would probably do that one at a 0.05 significance level. Whereas if it was something with medication, a procedure medically, something that's more severe, if we were wrong, we might want to go to a 0.01 significance level. Usually in your question, they're going to tell you what the significant level is. But the common ones are 0.1, 0.05, and 0.01. Those are the ones we've seen already. Okay? The most common here, as it says, is 0.05 and 0.01. So the significant level, just like we've seen before, is denoted by alpha, is the probability. What that means is the probability that the test statistic will fall in the critical region when the null hypothesis is actually true. Well, that's a big statement there. So let's dissect that. In other words, we're making the mistake of rejecting the null hypothesis when it is true. So it's like 7.2. So if we're testing a null hypothesis, I think there's a better slide than just my drawing, and we are saying not equal to. It could be an area down here, or it could be an area up here. Okay, that alpha is the test statistic will fall in the critical region. Where's the critical region? Right here. Here is with my null hypothesis is true right there, anywhere inside of where the critical regions are not. Just like when we talk about being usual and unusual. Remember how we did that? So the alpha is how true and how sure I am that I would not fall in a critical region and reject that when it really is true. That's what my alpha, that's my level of confidence. I don't want to reject a null hypothesis if it really is true. So I want to have that level of significance level. So step 5 in this process is that I have to determine the test statistic that I'm going to use. Just like we did before, there's the Z and the T, right? Just like we had in 7.3. We had to decide if we were using the Z or the T, correct? Same things hold true. If it's a proportion, by the way, the cards was a proportion. It was a percent, right? It wasn't a mean. Then I know I'm going to use my Z-score. I'm going to use my Z-score, the normal good old Z distribution, okay? There's our way of calculating it by hand. We know we don't have to calculate it by hand, right? We still have to know that there's at least the number of things we've got in our sample times the proportion that is true has to be greater than or equal to 5, and the number of items times Q, which of course is the failing part, has to be greater than or equal to 5. So proportion is Z. When we get to 8.4, we'll be doing the hypothesis around a mean. A mean, we're going to use the T instead of the Z if, just like before, sigma is not known. Back in 7.3, if sigma was not known, we use the T statistic instead of the Z. Same thing holds true. What also has to be true is it's either normally distributed, the population, or my N is greater than 30. Okay? Then I would use my T. For a mean, I will use my Z when it's known, when sigma is known. And this one was just left over on the chart. I didn't delete it, but the standard deviation or variance, it has to be normally distributed, and we're going to use a test called the chi-square. And if you take Stats 2, we use chi-square. We don't use that in this particular course. Okay? So kind of ignore that part for now. Okay, the test statistic is a value used in making that decision about the null hypothesis. Is it in a critical region? Is it not in a critical region? And it could be, we got to find the Z's scores that are associated with it. Step 6. Find the test statistic, whether it's Z or T. And then we're going to find the critical values or the p-value. The p-value. Okay? The p-value is nothing more than the area in the tail that would be rejected. So here we are back to the example of the X-sort. Preliminary results from the test of X-sort method of gender selection involved 100 couples. Is it over 30? Yes. This is a proportion. So right now I know I'm going to use Z. That's how you're going to determine. It's a proportion. I'm going to use Z. Is it normally distributed? It doesn't really matter because it's already over 30. But it is normally distributed. Okay? 58 were girls and 42 were boys. Given the preliminary result, calculate the value of the test statistics. Use the format of the test if I can speak this morning, statistic given the above so that the normal distribution is used to approximate the binomial distribution. So here we go. We said this is going to be our null hypothesis. We're going to assume you got a 50-50 chance of having a girl and a boy. Then the alternative hypothesis is based upon what was said. It said that the X sort would give girls more likely. So that's why we said the proportion would then be greater than 0.5. Then it's going to tell us that work under the assumption, of course, that it's 0.5. And then this is the sample. That's why we're using p hat. That's the actual sample. I have 58 out of 100, or 58%. So I can use that to do my calculation to get my z-score, because z would be what I use for proportion. Okay? We already know that a z-score of 1.6 really is not that unusual. So at first glance, it looks like X sort's not really going to make a difference. So here's what has changed from what we've done so far this semester, is the tails. Because you can have a one-tailed test or you can have a two-tailed test. You can have a one-tailed test or a two-tailed test. And whether it's one-tail or two-tail determines the p-values and critical values that are affected by that critical region. So the first thing we need to do is characterize hypothesis test as a two-tailed, left-tailed, or right-tailed test. The one we did with the cards. Make it a little smaller so I can get all three examples on here at once. And these are my critical regions. This is going to be a two-tailed test. And it's going to be when the alternative hypothesis uses not equal to. When the alternative hypothesis is not equal to, I have a two-tailed test. When the alternative hypothesis uses greater than. When it uses greater than, like the X sort method, it's more likely to be girls. Greater than, what do you think? It's going to be a one-tailed test. Is it going to be down here or up here? It's going to be to the right. This is my critical region in one tail because my alternative said greater than. Okay? And of course, this is still a one-tailed test. And it's when my alternative says less than. That's the only three symbols that I can have in my alternative hypothesis. Less than, greater than, or not equal to. And that's what determines what type of tail I have. Either a two-tailed or a one-tail, and the one-tail it's either greater than or the other tail less than. okay? This is why when alpha it's equal to or not equal to, it's divided equally in the two regions, because I don't care if it's less than or greater than. I'm just saying it's not equal to. So it's shared. It's divided into those two tails when I say not equal to. Left-hand tail, when it's down here, it's all of alpha is all in the left-hand tail. And of course, greater than alpha is all in the right-hand tail. So that p-value, or the probability value, don't get it confused with a proportion, right? We got lots of p's flying around. The p-value, and write it that way as p-value every time, so you do not get confused with p as your proportion, or p hat, which is what? Our proportion of our sample. So lots of p's flying around. So label, 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 okay? And our p-value is the probability of getting a value of the test statistic. This is as least as extreme as one of the sample data. So in other words, am I rejecting or not rejecting that null hypothesis? Is it in that critical region? So here's the p-values. Critical region is in the left tail. The left tail means it would be less than, right? Left tail less than. The p-value is equal to the area in the left of the test statistics. Okay? Critical region in the right would be the area, again, to the right. I said p-value is nothing more than area. And the critical region in two tails, the p-value is twice the area in the tail, because there's two tails. So when we did this and we found our statistic, our test statistic C was 1.6, has an area of 0.0548. If we looked at our z-table or we went to our calculators to find that area, we would find it 0.0548. The p-value then of 0.0548, and if we were testing an alpha of 0.05, it would not fall into that, right? It would be more in the null hypothesis area, correct? Am I losing some of you on that part? So we ran through our numbers, the proportion of the sample minus the actual proportion, divided by the square root of p times q over n. We found z to be 1.6. So if I go to my table and say z is 1.60, okay? The area, when I look it up, my area under the curve in that tail, this area right here, we would find to be 0.0548. That would be my p-value of this particular example. Now, if I'm testing at a 0.05, I would fail, correct? Why? Because if I was at the alpha of 0.05, my critical value would be here, but this falls, it falls in here, doesn't it? So here is where, this was a one-tail test, so here's where my null hypothesis is. I would fail to reject that. I would fail to reject it. So this is the procedure for finding your p-values. left tail and right tail. We know how we can do that. It's going to be left of the test statistic, right of the test statistic. But if it is a two-tailed, okay, it has to be right in the center. P-value is twice if it's that. Critical region. Same thing. I can use the critical region value method, or I can use the p-value method. Either one will give you the same result. The critical region is a set of all values of the test statistic that is where I would reject. Okay? And the critical region is any value that separates the critical region from the values of the test statistic that do not lead to rejection of that null hypothesis. The critical values are going to be your z-scores or your t-scores. The critical values are going to be your z-scores or your t-scores. Throws a lot. This makes you put it all together. We've learned a lot already this semester, and it's making you put it all together. Critical values are your t's or your z's. Okay? Depending upon your level of significance. So if I use the critical value method to have an alpha of 0.05, my z would have to be 0.1645. Would be out here, but the actual one came out to be 1.6. So 1.6 falls in the null hypothesis, so I would fail to reject the null hypothesis. If my z for my test statistic was 1.8, I would be out here in this critical region. And if I fall out here in this critical region, then I can reject the null hypothesis. If it falls within here, I fail to reject my null hypothesis. And here I just remind you, don't confuse the p-value with the portion p or p hat, which is the proportion of the sample. Write it, label them correctly. If you're using p for proportion, just put a p. If it's p hat, make sure you put the hat on it, because that's the sample. And anytime you're working with a p-value, take the time to write p-value. Don't get confused between all the p's. Lots of steps in this, huh? Depending on whether we're going to use the p-value method or the critical value method, it doesn't matter. We're still going to come to the same conclusion. Where we'll either reject or fail to reject the null hypothesis. We are not proving anything again. This is not a test to prove. It is a test to reject or fail to reject the null hypothesis. And that's all we can come out and say. So it's all going to be depending if it's going to fall into that critical region or our p-value. So again, it goes back and tells you again, our p-value came out to be 0.0545, something like that. Well, I could fail to reject based upon that. And because my test statistic was 1.6, my critical was 1.645, again, it fell in the null. So we have to write a final conclusion. We have failed to reject. We have failed to reject the null hypothesis. The null hypothesis was that we had 50% boys and girls. That's what we did in our test. So the way we can state our conclusion for the XSORT baby gender test, there was not sufficient evidence to support the claim that the XSORT method is effective in increasing the probability that the baby girl will be born. There is not sufficient evidence to support the claim, because the claim was you'll get a higher percentage of girls. Okay? It's like mud, right? I get it. Here's the wording of your conclusion.
So even though we failed to reject it, it's still
We can't support.
not sufficient evidence because it's so close to that.
Well, that's how we're always going to state it. Yeah. Yeah, so here's how you're going to state your conclusions. First, does it contain the condition of equality? What do I mean by that? The original claim contains the equals. And then if so, do you reject? Yes, there's sufficient evidence to warrant rejection of the claim. Or we say there's not sufficient evidence to warrant rejection of the claim. If the original claim does not contain equality and becomes our alternate hypothesis, in other words, with the girls, it says this will be more likely girls. That was a greater than. Because that was a greater than, this is where we're going to state our conclusion. If we reject, the sample data support the claim that, blah, the XSORT method supports the claim. If no, there is not sufficient evidence to support that claim. So then it goes back to the claim. And that we will practice. That we will practice, okay? We're going to practice all of it. I think we're close to the end here, and then we're going to get some practice in. Never conclude a hypothesis test with a statement of reject the null hypothesis or fail to reject, because you need a conclusion that people can understand. Always make sense of the conclusion with that statement that seems non-technical. And it has to address the wording of the original claim. So then we go back to, we are not proving the null hypothesis. We're either rejecting or failing to reject. Type errors. We're gonna come back to type errors because I want you to get some practice first on just even writing claims, using the claims to write the hypothesis and write the alternative hypothesis. So we're going to stop here and then come back to the type of errors.